Hello students, welcome to fourth lecture of D and F block elements. So in previous lecture we discussed about ionization enthalpies, and next point is related to ionization enthalpy. When atoms of metal gets ionized, they will produce positive ions. So now in this unit, in this lecture we are going to discuss about oxidation states of these metals. So oxidation of first row elements are mentioned here in the table. So as we can see, we have variety of different oxidation states in this case, and on the end side of this series, that means initial and last, initial first two and last two, these ions or atoms have limited number of oxidation states, whereas as we move from corner to center, we will notice that oxidation states are increasing. You will get different type of oxidation states, and number of oxidation states are also increasing. So reason for that is we have limited number of electrons at the starting of the series and ending of the series. So if we check the number of electrons in d orbital, then you will notice in first element we have 1 d electron, then we have 2, 3, 5, 5, 6, 7, 8, 10 and 10. These are the number of electrons in d orbital. As mentioned earlier, electrons in s orbital, that means 4s for first transition series, will be removed first, and then d electrons will be removed during the ionization reaction. So mainly different oxidation states depends on number of electrons present in the atom. So as we can see, we have limited number of electrons in initial state. That's why we have comparatively less number of oxidation state. Whereas as we move at the center, we have comparatively higher number of electrons to lose, and that's why we have comparatively more number of different oxidation states. And all the bold numbers actually represents normal or stable oxidation state of respective elements. That means remaining oxidation states are also possible, but they are not as stable as these bold numbers suggest. So plus 2 oxidation state are actually common for these elements, but stable oxidation states is a different thing. As we can see, in this case, Mn can show two different oxidation states, Mn plus 2 and plus 7. So reason for that is their stable electronic configuration. Main factor affecting the oxidation state is stable electronic configuration. Now let's check the oxidation states and the electronic configuration of Mn in this first and last plus 2 and plus 7 oxidation states. So we know that Mn is number 25, and outermost orbital configuration or electronic configuration for this is d5 4s2. So when it releases 2 electrons present in s orbital, you will get d5 electronic configuration. That's why plus 2 oxidation state of Mn is stable. Same thing when we remove all of these electrons, that means 2 from s and 5 from d orbital, then you will get plus 7 oxidation states. And as we remove the d5 electrons, you will get stable electronic configuration as 3p6. So it is stable electronic configuration. That's why this oxidation state of Mn is also stable. So for initial elements, we have less number of electrons. That's why we have limited number of oxidation state. But what about the last elements? Last elements have comparatively most electrons than the remaining elements of this series, but still they have limited oxidation state, and simple reason for that is stable electronic configuration. In copper and zinc, as we can see, we know that we have electronic configuration of 3d10, which is the most stable electronic configuration of all the other possibilities for d orbital. So they cannot release electrons present in d orbital easily, and that's why again we have limited number of oxidation states. So end of this series, that means initial part and end part, we have two different factors affecting in the oxidation state. For initial part, we have comparatively less number of electrons, and in later part, that means at the end of the series, we have comparatively more number of electrons. That's why orbitals are not empty for sharing. And this is the reason why we do not see comparatively more number of oxidation states in initial part and end part. The maximum oxidation state of reasonable stability correspond in the value of sum of the S and D electrons up to the manganese and followed by rather abrupt decrease in the stability of higher oxidation states. So the typical species to follow are Fe plus 2 and plus 3, CO plus 2 plus 3, nickel plus 2, copper plus 1 plus 2 and zinc plus 2. Variation or variability in the oxidation state is characteristic property of transition elements. If you compare the D blocks and P blocks, then you will notice in case of P block we have alternate oxidation states. That means, as for example, let's talk about the Cl. If you check the oxidation states, then it will be alternate in the number. As for example, chlorine normally shows -1 oxidation state, as for example in HCl or NaCl. Then we have 0 oxidation state in case of Cl2, and if we talk about the positive oxidation states of Cl, then you will notice it has +1, then +3, +5 and +7. Okay, so these are the oxidation states of P block element, and as we can see they are alternate. But if you check the D block elements, you will notice they are sequential, because D block elements gains oxidation state by losing electrons, whereas P block elements usually gains oxidation state by splitting the electron pair. As for example, in case of chlorine, how these oxidation states, positive oxidation states occurs. So if we check the electronic configuration for the Cl, then initially its p orbital contains total 5 electrons like this, and s orbital contains one pair of electron, and d orbital next to the p will be empty. But as we move from left to right in case of oxidation state, their electrons will start splitting. That means here it can form a single bond with a electronegative element. That's why it shows +1 oxidation state. When this electron splits and transfer into the d orbital, now 3 elements, electronegative elements, then the chlorine can combine and we have +3 oxidation state. Again, by splitting one more electron pair, you will get total +5 oxidation state, and by splitting the s orbital electron pair, you will get +7 oxidation state. In ClO4 minus, this ion contains +7 oxidation state of Cl. Whereas in Mn, we have this electronic configuration initially 4s2 3d5. So it will start losing the electron. In case of chlorine, electrons were unpaired, and that's why oxidation states were increasing. But in this case, electrons will be removed from the metal. Now why this type of differences occurred? Because P block elements are usually non-metallic elements, and non-metallic elements usually feel stronger attraction towards the electron, so they do not have tendency to lose them. Whereas Mn is metal and it can release electron because it is normal metallic nature. So if it releases one electron, initially it will release electron from s orbital. So when it releases these 2 electrons, it will get +2 oxidation state. And as we start removing electron from d orbitals, it will increase, oxidation state will increase up to +7 in KMnO4. Okay, if you check the oxidation state of Mn, oxygen normally carries -2 oxidation state, so total 4 oxygen will give us -8. Potassium gives +1 oxidation state. That means oxidation state of Mn should be +7, so total +8 equals -8, overall neutral. So that's why this variability arises. As for example, here example of vanadium is mentioned. It can show +2, +3, +4 and +5 oxidation state. All of them are sequential, whereas in P block elements they are alternate. You can get the example of oxygen as well. Oxygen can show -2 oxidation state in usual conditions, but it can show +2 and +4 oxidation state by releasing its electron up to +6 also. Now second thing in contrast with P block element is, in P block element lower oxidation states are favorable, that means they are more stable, whereas in case of D block elements higher oxidation states are comparatively stable. Reason for that, again same thing, P block elements are usually non-metals or semi-metals and D block elements are metals. So first thing, P block elements have stronger attraction towards the electron, whereas D block elements have weaker attraction towards the electron. And as we can see, example MO and W, molybdenum and tungsten, they can show very high oxidation state and they are stable. And here chromium 6 is also mentioned, but chromium 6 is comparatively less stable than the other two. That means heavier elements. Thus, chromium 6 in the form of a dichromate in acidic medium is stronger oxidizing agent, whereas MoO3 and WO3 are not. Oxidation nature depends on self-reduction. That means if it can attract the electron from the other element, then it will be reduced and other element will be oxidized, and our substance or atom or ion are considered as oxidizing agent. And low oxidation states are formed when complex compound has ligands capable of pi acceptor character in addition to this sigma bonding. For example, nickel CO4 and FeCO5, the oxidation state of nickel and iron is 0. Although they are connected with 4 and 5 other elements, it still shows 0 oxidation state because this ligand is neutral ligand. And pi acceptor characteristic, that means these metals will have comparatively empty orbitals available to share with other elements. And CO contains unpaired electrons which can be donated in these metals. And because of these, CO type ligands are strongest ligand. You will learn about it in coordinate complex compounds in detail. Next point, trend in the M plus M standard electrode potential, that means plus 2 to 0 oxidation state or reduction. So this is reduction potential. In table 8.4, thermochemical parameters related to the transformation of solid metal atoms to M plus ion in the solution and their standard electrode potentials are mentioned. So you can compare those values with this table or graph mentioned below. So in this table, as we can see, expected or calculated values versus observed values are mentioned. So majority of them are very close or exact the values of calculation, but we have two exceptions which we can see, cobalt and nickel. Now copper shows comparatively higher value of electrode potential. So these values actually represent reduction potential, and all of the metal except copper has negative values, that means lower than 0. Only copper has positive value of reduction potential. And we know that in electrochemistry it was mentioned as 0.34. So as we can see, it is the only element which shows positive value of standard electrode potential, and all the other remaining D block elements or first D block element shows negative value. So we can say that we can conclude that copper is normally reducive in nature, whereas all the other metals follows oxidation reaction. So we can say that copper is reduced, that's why it will behave as oxidizing agent, whereas all the other metals normally will behave as reducing agent because they will follow self-oxidation. Reason for the positive value of the copper is it cannot liberate hydrogen from the acid. We know that when we place copper and hydrogen in the same cell, that means when we conduct a cell having H2 and Cu, two different electrodes, then hydrogen has 0 value of electrode potential, whereas copper has comparatively higher value 0.34. And as we know, higher value follows cathodic reaction, lower value follows anodic reaction, that means oxidation, whereas copper will be reduced. So it cannot liberate hydrogen from the acid. That means H2 to H plus, that means it will be oxidized. For copper, our reaction will be Cu2 plus to Cu, that means it will be reduced. That's why it has positive value. So here thermochemical data are mentioned and their values are also mentioned, so you can compare. Next, trend in M plus 3 to M plus 2 standard electrode potential. An examination of electrode potential plus 3 to plus 2 values, that means it is again reduction but with different oxidation state, shows the varying trend. The low value of scandium reflects that the stability of plus 3, which has a noble gas like electronic configuration. Now if you check the electronic configuration of scandium plus 3, then you will notice no electrons are present in s and d orbital. Chromium is the first element of 3d transition series, so its electronic configuration is 4s2 3d1. So when we remove 2 electrons from s orbital and 1 from d orbital, you will get 3p6 electronic configuration, which is noble gas like electronic configuration. So obviously it will be stable one. The highest value for zinc is due to the removal of electron from the stable D10 configuration. Now when we remove 2 electrons from the zinc, you will get Zn plus 2 ions, and these 2 electrons will be removed from 4s orbital. So electrons of 4s are removed. That means zinc plus 2 have 3d10 electronic configuration, and this is the most stable electronic configuration for d orbitals. So removing electron from the highest stable highest stable electronic configuration is hardest. That's why it shows a rise in the value. And same thing is applicable with Mn, because in Mn plus 2 we have d5 electronic configuration, second most stable configuration for d orbital, and that's why it is again high. Whereas comparatively low value of Fe shows extra stability of Fe plus 3, again stable electronic configuration. The comparatively low value of V is related to stability of V2 half-filled T2G levels. Now what it means, as we can see, it is mentioned in unit 9, but still let's talk about it quickly. So stability of different oxidation states actually depends on electronic arrangement. Mainly it depends on electronic arrangement. So some of the stable electronic configuration for d orbital is d10 and d5. These two are most stable electronic configuration. Highest stable will be d10, second highest will be d5. But still we have some other oxidation states of the d orbital which are stable, but not in normal conditions, in specific conditions only. As for example, when these 3D transition metals forms complex compounds, then they have two different type of d orbitals in the same category. That means in 3D orbital it will split in two different parts. One part is called T2G orbitals and second part is called EG orbitals. So T2G orbitals, that means all the orbitals which are between the axis orbitals. That means dxy, dyz and dxz. Whereas EG orbitals are on axis orbitals. That means dx square minus y square and dz square. So that means same 3D orbitals will split in two different parts, T2G and EG, between the axis orbitals and on axis orbitals. So depending on the structure of the molecule, that means we are talking about some complex molecules formed by our metals. Okay, it is not in free state, they are in complex compound form. So depending on the type of compound, these two orbitals will be generated from the equal energy containing d orbital. Let's say initially we have same energy of all these 5d orbital. Now there are two different possibilities of the molecule formation by the metals. First, they may form octahedral molecule or they can form tetrahedral molecule. We are talking about the shape of molecule. Let's say if we have tetrahedral molecule, then the splitting of these 5 same energy containing orbitals will be something like this. We know that octahedral molecules are symmetrical, and let's say these are the axes x, y and z. At the center we have our metal M. Then all the ligands or attachment with our metal, if it is octahedral, will be on axis. That means suppose this is the first, second, third, fourth, fifth and sixth. 6 different ligands are attached with our metal and all of them are present on axis, so their electrons. Okay, so their electrons are also present on axis. That's why this electron will repel the electron present in d orbitals, and because of this, orbitals present on axis will feel higher repulsion. Higher repulsion, that means higher energy. So on axis orbitals will increase their energy and between the axis orbitals will decrease their energy. So we have higher energy orbitals here and lower energy orbitals here. Now let's say compound is tetrahedral. Then all the tetrahedral bonds are actually between the axis bonds like this. Okay, so this thicker line represents tetrahedral molecule. At the center we have our metal and we have ligands between the axis. So obviously now between the axis orbitals will feel more repulsion of electrons of ligand because they are comparatively closer, and on axis orbitals will feel less repulsion. So on axis orbitals will lower their energy and between the axis orbitals will increase. That means Eg orbitals have lower energy than T2G in this case. This raises new stable electronic configurations. That means if we have octahedral molecules, then initially same energy containing 5d orbitals will split in two different parts. We have comparatively lower energy containing T2G orbitals and higher energy containing Eg orbitals. So that means if electrons are present in this orbital, then D3 electronic configuration will be also stable electronic configuration. So same thing is going on with V2 plus. It has half filled T2G levels. That means it has D3 type of electronic configuration in one of the electronic configuration when we have V2 plus. And this point will be discussed in detail later again. Next is a trend in stability of higher oxidation states. So higher oxidation state usually can be achieved using strong electronegative elements. Now why we need strong electronegative elements? Because as we remove the electrons, nuclear positive charge will be more and more dominant. So to removal of electron we need some stronger elements to react with. Otherwise removal of electron will be comparatively very hard. Although these are metals, but if we remove more and more electrons, their nuclear charge will be comparatively higher effective and electron removal will be extremely difficult without any support of stronger elements like F. So in table 8.5 the stable halides of the 3D series are mentioned. The highest oxidation numbers are achieved in TiX4 and it has 4 elements, that means it is tetrahalide V5 and CrF6. So plus 7 state of Mn is not presented in the simple halide, but it has MnO3F type structure, and beyond the Ml except Fe and Co no other has trihalides. The ability of fluorine to stabilize the highest oxidation state is due to the either higher lattice energy as in case of COF3 or higher bond enthalpy term for the higher covalent compounds, example VF5 and CrF6. Overall main reason is F is strongest electronegative element. So that's why all this term mentioned here can be achieved using fluorine. Although V plus 5 is represented only by the VF5, the other halides however undergo hydrolysis to give oxohalides. That means oxygen is also present and we have halogen compound. Another feature of the fluoride is their instability in the low oxidation state, example VX2. And the same applies for CuX. On the other hand, all the Cu plus 2 halides are known except the iodine because copper plus 2 oxidizes I minus to I2. So, however, many copper 1 complexes are unstable in aqueous solution and undergoes disproportionation. Disproportionation, that means from the single reagent you will get two different products having higher and lower oxidation state than the reactant. As we can see here, we have plus 1 oxidation state of the reactant and plus 2 and 0 oxidation states of products. So this is called disproportionation reaction. The stability of Cu plus 2 rather than the Cu plus is due to the much more negative hydration enthalpy of the copper plus 2 than the copper plus, which more than compensate the second ionization enthalpy of copper. Because if you check the electronic configuration of copper plus 2, then you will notice it is D10, one of the highest stable oxidation state electronic configuration. But still copper plus is less stable than copper plus 2, and reason is mentioned because of negative hydration enthalpy. The ability of oxygen to stabilize the highest oxidation state is demonstrated in oxides. Now usually oxygen is one of the most electronegative element and is divalent. That means it can form two bonds. Whereas F fluorine is also highest electronegative element, but it is limited to one bond formation. It is monovalent. So that's why you will notice most of the cases oxygen is able to achieve highest oxidation state, or number of highest oxidation state with oxygen is more than fluorine. Reason, simple reason, it is divalent. It can form two bonds. So the highest oxidation number in the oxides in table 8.6 coincides with the group number and is attained in scandium 2O3 and Mn 2O7. Beyond group 7, no higher oxidation states or oxides are available above Fe2O3. Although ferrate, that means Fe plus 6, is possible, but it will readily decompose in Fe2O3 and O2. Besides the oxides, oxocations, that means oxygen containing positive ions, are stabilized V5 as VO2 plus and V4 as VO2 plus, and Ti plus 4 as TiO2 plus. The ability of oxygen to stabilize these high oxidation states exceeds than the fluorine. Thus, the highest Mn fluoride is MnF4, and for oxygen it is Mn2O7. That means for fluorine you will get plus 4 oxidation state of Mn maximum. Whereas with oxygen we can achieve plus 7 oxidation state. Reason, again, it is divalent normally. So ability of oxygen to form multiple bonds to metal explains its superiority. In covalent oxides Mn2O7, each Mn is tetrahedrally surrounded by oxygens including MnO-Mn bridge. And tetrahedral metal oxides, 4 tetraoxides, are known for vanadium, chromium, manganese, 2 different and 3 different state of manganese. So structure of Mn2O7 will be something like this. They have a bridge of oxygen and each Mn contains 3 oxygens and a tetrahedral shape around it. That means if we check the Mn, then you will get a tetrahedral shape around it by oxygen. So we have two different tetrahedrals attached with each other like this. And bridge oxygen will have single bond with both of the Mn, and these end Mn oxygens have double bonded with Mn.